Hey everyone, this is the fifth part of Man tutorial series, where we will explore ODEs to animate 3D strange attractors. So far, we have been working within the confines of a two-dimensional space. Now, it is time to break free from that box and explore the vast possibilities of three-dimensional world. This is a world of animation, and in this world, knowing how the camera is oriented and placed in the three-dimensional world is very crucial. This knowledge allows us to decide the most captivating view or angle for our audience to experience the scene. You see these angles here, theta, phi and gamma at the left upper corner of your screen? These are called Euler angles. These angles are shown in radians. Now, the code to orient the camera frame is quite straightforward. You can set the orientation of the camera either by using the function set Euler angles or the reorient method. Let's just take a closer look at what each of these Euler angles mean. To help us understand better, to visualize it properly, I am adding another set of axes so that we can see what actually is happening. Consider this red axis as being attached to the camera. So the camera rotates, it rotates. One of the easiest Euler angles to understand is a gamma angle. Imagine a line stretching from the camera to the origin. If I rotate the camera about this yellow axis, the amount of rotation is our friend gamma here. Moving ahead, next, we have Euler's second angle, phi. Here, the rotation of the camera is about the x-axis, and the phi is the amount of that rotation. Lastly, we have theta, where the rotation is about the z-axis. Now, you might notice that the gamma and theta, they look similar. When I described the gamma initially, notice that phi was set to 0, which means that yellow axis coincides with the z-axis, which means that gamma and theta behave in a similar fashion. But if I give some value to phi angle here and align my camera with the red axis, observe the rotation when I change the gamma angle. In this case, the gamma and theta, they behave in a different manner. You remember in my previous tutorial how we used to draw a sine function with a parametric curve? Well, this time let's make a spiral, specifically a vertical helix. The function in the parametric curve would be sine t, t and cos t along the x, y and z axis respectively. In 3D, Manim would have some rendering issues, as you can see here. And to make it more vivid, we need to set the flat stroke to false. But still, even with this adjustment, the curve appears a bit rough. The key reason behind that is the step size, which determines how the points are arranged along the curve. To visualize more clearly, these dots here come with the step information of the parametric curve, of the parametric function. The points are arranged as specified by the tfunc argument, and the space between them can be adjusted with the help of trange argument, basically the step size. So to improve this, I need to decrease the step size to generate more points, making the curve smoother. However, the downside of generating more points is that it increases in the computational power, as was the case with the 2D sine curve. Let's move ahead to simulate the strange attractor. The very first explanation of a chaotic system was demonstrated by Edward Lorenz by explaining the butterfly effect or the Lorentz attractor. The equations of this chaotic system are defined by these ordinary differential equations, ODEs for short, in x, y, and z dimensions, which creates such butterfly-like structure. The dot here represents a derivative with respect to time. Notice that these equations are implicit, and to plot such equations in MANIM, we need to modify these differential equations. A greedy way to approach this problem is to treat them as a kinetic equation. Take the equation of x dot for example. For simplicity, let's assume v equals sigma of y minus x. This way I can transform dx by dt equals to v, and then dx equals to v dt. This dt acts as a step size in our code. Now dx will be equal to the change in position in x direction, which equals to x minus x naught. Following the process, the new position x will be equal to the old position x naught plus v dt. But even if we do this, remember the time step has to be small enough to make the curve smoother, and that constitutes to a large computational power, especially in 3D animations, and not to mention the space complexity. To overcome such complexities in the code, there are numerous computational methods to solve such problems, to solve ODEs, and those methods provide the same degree of accuracy in an efficient manner. Well, to solve our ODEs, I will be using these two popular methods, which can be implemented with the help of SciPy's method solve IVP from its integrate module. Let's first see how can we code the greedy approach. So after defining a class, in these 4 highlighted lines, I am assigning class attributes for initial position, the number of points, the simulation time, and the constants of ODEs, basically the sigma, beta, and gamma. In the line 8, I am setting the camera orientation. Here theta is 45 degrees and phi is set to 60 degrees. And in this line, I am getting the Lorentz curve from a function which we will see in a minute. And the next 2 lines decorating the curve. And further, I'm animating the curve with show creation. Now let's focus on the crux of our code, the function getLorentz_curve. In the second line of this code, I'm defining a matrix. You see, every row of this matrix is a location of a point as x, y, and z coordinates of a canvas. The first row of this matrix is set to the initial position that we defined as class attribute. And then, as I demonstrated, dt here acts as a step size. So essentially, the evolution of the Lorentz attractor is being saved as an array of points. A matrix where every row is the updated position of its previous row. These highlighted lines here describes a simple for loop that saves the evolution steps or the evolution of the strange attractor as the time progresses. The update curve function returns our respective x dot, y dot, and z dot terms of the Lorentz equation. And then I am updating the position of x, y, and z coordinates. Moving ahead, in the parametric curve, we need to tell MANIM where to look for the points to plot the curve. The function argument returns an array of x, y, z coordinates at every index I, and which goes from 0 to the number of points minus 1. And that index I is defined by the drange argument. And I want to point out one thing is that the step size is not equal to 1 here. You see, every row in the points matrix is an updated version of its previous row. And the step size between these two consecutive rows is dt actually. The drange argument actually returns an array where the elements goes as 0, 1, 2, and so on, up to the number of points minus 1. And the last piece of code, which is update Lorentz function, which is just returning the result of differential equations of Lorentz attractor. Now you notice the parameters t and position are set in this specific order so as to serve our improved version of code, which is implementing the solve ABP function from the SciPy package. Now, to achieve the computational efficiency, we need to modify our getLorentz curve function. And that's why I'm inheriting all of the code from Lorentz abstractor scene class. The first line of this function is dt. That's I have already described. The next piece of code sets a parametric curve. I guess the t-range argument is straightforward. Here dt is a time step. Now in the function argument, I'm returning solution.sol of t, which actually provides coordinates of a point x, y, and z at any time t. For instance, at any time t equals 0, it gives me the initial position of the curve, and at t equals 2 seconds, it gives me another location of the curve. And this magic is due to this method, solve ABP. The first argument in this method is a function itself, update Lorentz, and that we have already covered. The second argument tspan is a range of the time of our simulation, which goes from t equals 0 to t equals simulation time that we defined as a class attributes. The third argument y0 is the initial position of our curve. And the fourth argument, dense output, must be set to true to get the solution at any time t. Well, I guess this is how we plot any ordinary differential equations. So I went ahead to experiment with some of the attractors that I'd like to show you. I'd like to take a moment to thank you for watching this video. I hope you learned something unique today, something new maybe. And if you did, do not forget to hit that like button. And I'll see you in the next video.